This is a guide to L'Hopital's rule by Arav, Tommy, and Zach. L'Hopital's rule is used when evaluating the limit of a function in indeterminate form. When plugging the value of the limit into the function, an indeterminate form would be shown as 0 over 0 or plus or minus infinity over plus or minus infinity. For example, let's look at the limit as x approaches 0 of x squared over sine x. When plugging 0 into this function, the limit of the top would be 0 and the limit of the bottom would also be 0. Since both the top and bottom functions equal 0 when x approaches 0, L'Hopital's rule can be applied. Remember that to prove that L'Hopital's rule can be applied to FRQs, you must take the limit of the top and bottom separately. You may not show that the function is equal to 0 over 0. How do we use L'Hopital's rule to determine the value of an indeterminate limit? If the limit of both the top and bottom functions is equal to 0, we must find another way to evaluate the limit, which is where L'Hopital's rule comes in. We can evaluate an indeterminate limit by taking the derivative of the top function and the derivative of the bottom function and plugging the limit of the x value back into the two functions. Let's walk through an example. The limit as x approaches 0 of e to the x minus 1 over x. First, we verify the indeterminate form. If we plug in 0, the top becomes e to the 0 minus 1, which is 0. The bottom is simply 0. Because the function evaluates to 0 on the top and 0 on the bottom, we can apply L'Hopital's rule. We take the derivative of the top function, e to the x minus 1, which just gives us e to the x. Then we take the derivative of the bottom function, x, which is just 1. Now we plug our limit of 0 into our new expression, e to the x over 1. Evaluating e to the 0 gives us 1, leaving us with 1 over 1, so our final answer is just 1. Using L'Hopital's rule multiple times. If L'Hopital's rule is applied and the limit is still indeterminate, we must use L'Hopital's rule again until we get a limit not of indeterminate form. Let's look at an example. The limit as x goes to 0 of 1 minus cosine x over x squared. First, let's plug in 0. The top becomes 1 minus cosine 0, which is 1 minus 1, which equals 0. The bottom becomes 0 squared, which is also 0. Since we have the indeterminate form 0 over 0, we apply L'Hopital's rule and take the derivative of the top and the bottom. The derivative of 1 minus cosine x is sine x, and the derivative of x squared is 2x. Now we evaluate our new limit, the limit as x goes to 0 of sine x over 2x. Plugging in 0 gives us sine 0 on top, which is 0, and 2 times 0 on the bottom, which is also 0. We are back at 0 over 0. Because the limit is still indeterminate, we must apply L'Hopital's rule again. The derivative again, the top function sine x becomes cosine x, and the bottom function 2x becomes 2. Our new expression is cosine x over 2. Now, when we plug in 0, we get cosine 0 on top, which is 1 over 2. This leaves us with a final answer of 1/2. Let's look at how to apply L'Hopital's rule purely from a graph. Here, we want to find the limit of tan x over x as x approaches 0. Look at our first graph on the left, which shows f of x equals tan x and g of x equals x. As we trace both functions towards an x value of 0, they both intersect right at the origin, giving us a y value of 0. This gives us our indeterminate form of 0 on the top and 0 on the bottom, meaning we can use L'Hopital's rule. Next, we need to evaluate the ratio of the derivatives at the same point. Our second graph on the right shows the derivatives f prime of x equals secant squared x and g prime of x equals 1. If we look at x equals 0 on the graph, g prime of x is a constant horizontal line at y equals 1, and our f prime of x curve also hits the y-axis perfectly at 1. L'Hopital's rule states that the limit of our original functions is equal to the ratio of the derivatives. so we simply divide f prime of 0 by g prime of 0, which is 1 over 1, giving us a final answer of 1. Solving a limit using L'Hopital's rule from a table is mostly the same as with normal functions. You check for the indeterminate form, take the derivatives, and use the table to find the necessary values to evaluate your new expression. Let's solve the limit as x approaches negative 3 of f of quantity 2x minus 1 over x squared minus 9. First, we check that the limit is indeterminate when x equals negative 3. For the numerator, plugging in negative 3 gives us f of negative 7. Looking at our table, f of negative 7 equals 0. For the denominator, negative 3 squared minus 9 is also 0. Because we have 0 over 0, we can proceed with L'Hopital's rule. Next, we take the derivative of the top and the derivative of the bottom separately. Using the chain rule, the derivative of the top is f prime of 2x minus 1 times 2, and the derivative of the bottom is simply 2x. Now, we evaluate these new limit expressions by plugging in our x value of negative 3. On the top, we get f prime of negative 7 times 2, and given our table, that gives us 12. On the bottom, evaluating 2x at negative 3 just gives us negative 6. Finally, we just divide our numerator result by our denominator result, and 12 divided by negative 6 leaves us with the final answer of negative 2. To wrap things up, we have one final assessment question for you to test your understanding. Try evaluating the limit as x approaches 0 of e to the x minus e to the negative x minus 2x over quantity x minus sine x. We hope you enjoyed our guide to L'Hopital's rule, and thank you for watching.